This should be Chem28BBlake. And I'm continuing with page 289 and onward, classifying chemical reactions. So this is an extension of what we were doing off the worksheet, an extension of what we were doing past number 13. I think the first few up to 13 was more or less about balancing equations. And these kind of go together. So number 14, you know how to do the types, so I should be able to go right into the questions. 14, the solids aluminum and sulfur react to produce aluminum sulfide. So what you have here is Al solid plus S solid gives you Al2S3, which is solid. And you need to identify the type. Well, you're putting everything together to make one product, so that's synthesis. And when you balance that, I have 1 times 1 is aluminum, 1 times 2 is 2, so I need a 2 in front. I have 1 times 3 is 3 sulfur, so this needs to be 3 times 1 is 3. Interestingly, one could argue that this is a combustion because sulfur is, I would argue, I'm not sure how many people would agree with me, but here's the logic. Sulfur is right below oxygen. This reaction is also redox because aluminum is starting at 0 and its oxidation number, it's an element here, so its oxidation number is 0. Sulfur is an element here, its oxidation number is 0. Notice that I'm putting the oxidation numbers directly above. They're not charges. A lot of times they're equal to charges. And I'm putting them in blue. But aluminum is giving electrons to sulfur. So by oil rig, oxidation is losing. Aluminum is becoming Al3 positive as its charge. So its oxidation number is positive 3. So with an oxidation number, the sign goes first and then the number. With charges, the number goes first and then the sign, and the charges are written over here. This is not a charge. It's equal to the charge via the oxidation number rules. Let's see if I can find the oxidation number rules. The oxidation number of a rule 2. The oxidation number of a monatomic ion equals the charge on the ion. And that's what you have here. So the charge on this aluminum ion is 3 positive, so the oxidation number is plus 3. Sulfur is making the sulfide ion, which is a 2 minus charge, so its oxidation number is minus 2 each. So minus 2 minus 2 minus 2 is minus 6, plus 3 is plus 6. Together, in the compound, they are adding up to 0, which I think is rule 7. Rule 8. Sum of the oxidation numbers of all atoms in a neutral compound is 0. Same here. Sum of the oxidation numbers in a neutral compound is 0. Now, what I was saying about combustion. Sulfur is right below oxygen. Same family. If this was with oxygen, we would call it a combustion, as long as it was done at a high enough temperature that it went fast enough to give off heat and light. So just because sulfur is your oxidizing agent instead of oxygen, it can be combustion, I would argue, in a reaction like this. We don't know the specific reaction conditions to know if it's hot enough to give off heat and light to be a combustion, but it could be. Okay, so this is synthesis, but it's also redox because the oxidation number's changed. Okay, next one, 15. I set my glasses down somewhere I can't see. Here we go. Water and dinitrogen pentoxide gas react to produce aqueous hydrogen nitrate. There's water is H2O. Dinitrogen pentoxide gas is N2O5. Should know how to do that. Because of the name dinitrogen pentoxide, we know this is molecular. If it was ionic, it would be a different name. It would be nitrogen oxide. And it makes hydrogen-nitrogen gas. Aqueous hydrogen nitrate, sorry. If you call, that's weird. Because if you call HNO3 hydrogen nitrate, then you don't have it mixed with water. And it would be, I'm not sure what phase of matter it would be, actually. But if you're going to call it HNO3 aqueous and put it in water, then it's nitric acid. So to call it hydrogen nitrate aqueous is weird. It's nitric acid if you have it in water. I guess this does make a gas. If it was hydrogen nitrate, it would be a gas. I guess I did know that. Okay, so what type is this? Well, I'm making one thing, so it's synthesis. If we count out these oxidation numbers, they're not changing because the oxygens are -2 apiece. That's rule 4, I think. Let me go check. No, that's fluorine. Oxygen has an oxidation number of -2 unless, and this is not one of the unlesses. So that's rule 5. Oops. Uh-oh. I don't know what happened there. Oh, you have got to be kidding me. It shouldn't be the case where you can accidentally click a button and everything goes poof. This is why software people should face severe consequences for making things that aren't user-friendly and intuitive. Okay, back to this. Nitrogen, we don't know what its oxidation number is, but we know that total has to be 0. So if I have 5 -2s, -2, -2, -2, -2, -2, and I have to equal 0, and I have 2 nitrogens, what is this and what is this in order for all that to equal 0? Now this is not hard. So get that through your head. This is easy to do. It is not confusing, and yes, you need to do it, so just step up and do it. I always, right before the test, you have to say, how do you do that? Step up. You have 5 -2s, 2 we don't know, adds to 0, and you can do that math. And when you do that math, the nitrogens are +5 apiece. The oxygen here is -2. One of the rules for hydrogen in that table tells you it's usually +1, and here it is. Oxygen here is -2, -2, -2. Hydrogen here is +1. Again, this is not hard. So get that through your head. This is not hard. Equals 0 because it's a compound, -2, -2, -2, something for the nitrogen, and +1. I don't understand. Yes, you do. Hydrogen's +1, oxygen's -2 each, nitrogen's what? That adds up to give you 0. This is +5 again. So, the reason why I jumped through all those hoops is because we want to check to make sure it's not redox, not oxidation reduction. No oxidation numbers are changing, so it's not redox. Okay, it is, however, synthesis. And it wasn't balanced. I had 1 times 2 is 2 hydrogens, so when I put a 2 here, everything ends up balancing at that point. Okay, let's go onward. 16. We have NO2, and O2 is N2O5. All these are gases. I was making this when I dissolved that silver. Mixed with oxygen in the air, you can make that. I don't know what the reaction conditions are to have to do this reaction, but it could in theory make it. All right, that is synthesis. I have two things coming together to make one. You could call it a combustion, you know, especially if it runs hot enough to do that. It is also redox, because oxygen is in its elemental form here. So its oxidation number is 0. Here it's -2 each. So nitrogen has to be +4. What? -2 gives you 0. Over here, this was -2 and +5. So this is redox because these oxygens are changing to -2, and the nitrogen is changing from +4 to +5. So it is synthesis and it is redox. Okay, and then when you go to balance it, I have 1 nitrogen and 2 nitrogens, so I need 2 in front here at least. And then that gives me 2 times 2 is 4, 1 times 2 is 2, 2 and 4 is 6. That doesn't work over here. For one thing, I need to have an even number. So the only way I can get my even number is to make this a 2. And now I have 4 nitrogen. And what's that leave for oxygen? 4 times 2 is 8, 1 times 2 is 10, 2 times 5 is 10. So now it's done. So you have to split these oxygen in half. So you end up with an even number of them. This one does balance a little awkward. That is because it is redox. We won't get to it this year. The organic chemistry students are working with this now, but they're making balancing redox reactions. So it's more involved than the balancing we've done to this point. About this reaction, okay, at least we know this is double replacement. In a double replacement, you can write your water as HOH if you want, and then you can see it a little easier. Just to balance, I can see that I need a 2 here, so I have 2 sodiums, and that might do it. Yeah. So this is double replacement. I want to point out that we are not going to get into double replacement, I don't think, before the exam. I just found out the last minute information about the exam here less than probably a half hour ago, so I don't have any answers for you yet. But a reaction like this that's double replacement goes to completion under a few things. If it makes a precipitate that falls to the bottom, it'll go to completion. If it makes a gas that bubbles away, that'll go to completion. Or in this case, if it makes water and it's all occurring in water, aqueous, 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 it'll go to completion. That, in this case, this is the neutralization of an acid that starts with H with a base that ends with H. So if you make a precipitate, it goes to completion. If you make a gas that bubbles out, it goes to completion. And if you do a neutralization reaction between an acid and a base, it goes to completion. The other ones maybe do, maybe don't. Depends on solubility product, which we still haven't got to in organic chemistry yet, which we will. So that's why this says in double replacement reactions, when we go to study them, we're going to look at when they go to completion when a precipitate forms, from pages 38 to 30, I don't know what this says, 38, 35 to 39 for. These aren't page numbers. I'm not sure why this says this. Probably numbers 35 to 39. That makes more sense. If a gas is formed and you get effervescence, probably problems 45 to 49, those go to completion. And if you do a neutralization between an acid and a base, and you're going to form a salt and water, problems 40 to 44, it looks like, does go to completion. I want to go back and point this out because we will see this again later. Notice when I put my acid with my base, I get a salt, a positive and negative salt, and water. You always get a salt and water. Okay, next one. Aluminum oxide breaking down. This is the reverse of what we saw earlier. So this is a decomposition. It also happens to be redox because all the oxygens are -2 apiece here and they're 0 here because this is elemental form. Aluminum is 0 here and +3 there, oxidation number. So this is decomposition and redox. To balance it, we have 3 oxygen and 2, so I need 3 of these and 2 of these, which gives me 4 aluminum. This one here, nickel 2 hydroxide. If you heat it up, it will break down into nickel oxide and water. That is a decomposition. And that's it. None of the oxidation numbers change. Hydrogen is +1, oxygen is -2, nickel is +2. Here nickel is +2, oxygen is -2 each case, and hydrogen is +1. So no oxidation numbers change. And it's balanced. Let's see where we're going from here. Okay, more reactions. This is heating up baking soda. If you had a fire in the frying pan, you'd throw baking soda in there and it would make this reaction go. These are in the section right after decomposition reactions, which would make them decomposition reactions. You have one piece here, no plus sign, breaks down into multiple pieces. To balance that, already I can see I need a 2 on this sodium. And that would give me 6 oxygen. 1 times 3 is 3. 1 times 1 is 1. 1 times 2 is 6. That will give me 2 carbon. Okay, that's going to be messed up. Oh, I do have 2 carbon. There's 1 and there's 1. 2 sodium. Hydrogen would have 2. And there I have 2. So that is all fixed just by putting a 2 in front. Number 20. Okay, now we're going to get into the replacement, what your book calls replacement reactions, what they ought to call single replacement reactions. Single replacement reactions. Okay, and there is on page 293 this diagram. Tells you the activity series. Every time you do an activity series problem, it is a single replacement reaction that is involved. Notice, and I mentioned this in class on Tuesday for the people that were here, that if you start on the left of the periodic table, and by the way, there are not even probably 20 substances in here. This is not a very complete activity series. We could easily double or triple the size and put a bunch more metals in here and have an activity series. But for the ones that are here, notice we're at the left of the periodic table with the alkali metals with lithium, potassium, and sodium. Rubidium is also alkali metals. So lithium, rubidium, potassium, and sodium are alkali metals. Calcium and magnesium are alkaline earth metals in the second family. And then as you go to the right, you're going farther down to the table pretty much. You get to the center of the periodic table, gold is the least reactive. Now my point is this, these top 4 or 5 are so reactive, they will explode when you throw them in the cold water. Okay, calcium won't explode when you throw it in cold water, but it will react. The other 4 will cause an explosion. Okay, as you go down the periodic table, they get less and less reactive. Now my point in bringing this up is, you could write the reactions for these if they're aqueous, but that doesn't mean that it actually goes, because something else is going to happen. Just because you can write a reaction and balance it doesn't make it right. I sometimes have to point that out to students. Well, what's wrong with this reaction? Well, just because you can write it and balance it and all that, it doesn't mean it will actually work that way. Okay, this is a good place to stop. We're out of time on this video.